Okay, so today we'll be learning about how to fit Gaussian on the spectrum of the galaxies or stars, whatever, and find out the redshift out of that spectrum. Earlier, we were visualizing that spectrum, and through the interactive spectrum, we were finding the value of H alpha. Rather than that, for a lot of spectrums, uh, for the sample, we can't manually go to that particular section of that galaxy and find out the observed wavelength. Rather, we build a pipeline to automatically find out the observed H alpha wavelength. So for that, we need some Python program. So today we will be learning that only. So for creating the functions and Gaussian plot, basically we will be needing some uh, packages which are NumPy, then Matplotlib. Today's section will be much easier than what we did yesterday. So it will be all you have already done. So now there is one more thing, SciPy. There is one package in module in SciPy which help us to fit the Gaussian plot. It help us to kind of do fitting or linear regression and other stuffs. So we will be taking help of that to fit our values, our guess values to the Gaussian plot. So I will tell you where we will be using this package. So for now, I'll just import this, and when I will use it, I will tell how we are impacting, how it is impacting our code. So it's import like this. So from a scipy dot optimize import curvefit. Now we have to define a formula for define a function for this formula. So basically, just a second, we have double brackets here. Okay. So first we have to write this formula in the form of Python. So let's say the function is written as Gauss with the parameter as one we have unknown value x, and one we have this amplitude as unknown. Then we have to write this sigma value, and this then we have something called here mu value, okay, which is basically the mean or the center. So let me explain what is this formula. So basically lambda will be our wavelength for now. So I'll tell you, or flux, a will be the amplitude and mu will be the center of the peak, and standard deviation will be the width of the curve. For example, normal distribution. So for example, we have this normal distribution graph. I'll just open some images. So this is, for example, our normal distribution. Here is the mu, which is basically the peak value, the value at which the peak of the graph will be there. And sigma values are determine the width of the graph. And then we have the amplitude, of course, which is basically how much high this is. That is the peak height in total. Okay, so coming back to this, I'll tell you why I have written this lambda here soon. Now we have to assign some variables a, oh sorry, a, then we have sigma here, and let's write mean and sigma. We can write sig here for sigma. Then Gaussian formula as a divided by, then bracket sigma multiply by np dot square root, because we can write the square root using numpy like this, and then it was twice of pi. So it will be something like np dot pi. So yeah, we have written this thing here. So a by sigma times np dot square root 2 times of pi, and now after this bracket we have to again multiply. So now I guess this is the bracket. Yes. No, this one, out of this bracket. Then we have to multiply with exponential. We have to write it as this numpy dot exponential times minus of, then the upper part, which is basically x minus mean, times uh, to the power, sorry, 2, then divided by 2 times the sigma and 2. Yes, I guess. So if I'm not wrong, we have done it correctly. So it will take time to process. I guess we have missed something. Minus was okay. So this is the bracket for this. Then minus must be on whole of this. Okay. So yeah. So we are done with the formula. Then this function will return this whole value of quotient, whatever will be there by putting these parameters. Now let's test our Gaussian plot basically. So we will assign let x test is equals to numpy dot length space, then 0 to 20 and 100 points. So basically why we are learning to plot this Gaussian graph is because most of the spectrum are in the Gaussian forms. So we are using that fundamentals to learn and apply it on the main spectrum. So yeah, we have to like use Gauss test. This will basically we will assign these values x underscore test, comma, let's say our amplitude is 2 for now, then our mean is 5, and width is sigma value, that is the width of the curve is 1. Now I will just plot it as x underscore test, then with Gauss underscore test, and I will just do plt dot show. Okay, so I think the spelling is somewhere wrong. Okay, so yeah, so you see here it is a very beautiful plot with the same standard deviation amplitude at 5. So this we have our basic normal distribution. Okay, now we will be going to plot some same distribution with more peaks, so more than one distribution. Okay, so it will be a multi-Gaussian type of thing with two normal distribution in the one plot. So we will define a function, let's say non-linear, and we will write x underscore value because it will be same for all. This x value will be same here. Now we have to write these things. So since we will be having two plots, so there will be two amplitudes, two means, and one sigma for now, because I want the mean to be same, and there will be a continuum. So continuum is basically a minimum range after which we have to start the plot. So for example, here it is 0, it is assigned 0. If I assigned a continuum to be 1, the plot will start from 1 only. So now A1, A2, V1, V2, oh sorry, let's say mean 1, mean 2, and then width 1, and con cont for continue. Now return. In return, we will be basically returning that Gaussian, but as a sum of both, because we will be using the same formula of Gaussian, but this time there will be two normal distributions, so it will be the sum of both. So now x underscore win, comma a1, comma m1, comma v1, w1 plus cos, because you see a1 m1 w1 will be for the first plot, and x underscore values will be same for both of these, because x-axis will remain same, a2, and then we have m2, then we have w1, and all of it will be after some continuum level. Now I will run this. It ran successfully. Now I have to test it. So I will write capital Z underscore test will be is equal to numpy dot len space, then 0 to 20 same range and 100 points, let's say. Then y values will be the Gaussian values basically for this plot, which is for this function which is non-linear now. And now we will be assigning the values, which is basically x value will be x test values, x test values. So I am just calling this function here with the x values as x test values, and a1 let's say 1, a2 is equal to 2, and median 1 and mean 1 and mean 2, let's 5 and 10, let's say 5 and 10, and then 1 and 2, width as 1 and the continuum as a 2, or let's say 3 for now. I'll show you what's the difference it will be creating. Now I will just plot x test comma y underscore value. So it gave me an error because it's a, okay. So again, I messed up with the spellings here. So I have to just write here properly. So you see, we have this plt dot show. So okay, so we have two Gaussian plots here, for two normal distribution here. So basically, what we are doing is just like sine and cos curves, we are just plotting the Gaussian curve. Gaussian curve also have some function, and we are applying the same function to this thing. Okay, just like we did for the matplotlib section when we defined sin x and tan x and cos x functions. So similarly, we are first defining the function in this Python function. As a function, I mean this function. As a Python function, I mean this whole function. Okay, so I am defining this function as this Python function, and then assigning some values to the parameters, and then finally plotting it. Okay, so to see if it is validating our function or not. Now we have to make something now. So today's lecture will be short because we don't have much to do today. We have to study the Gaussians, and after that we will be learning about how we can uh, take the real world data and fetch these redshift using the Gaussian profile. Okay, so now we have to make a journal model. Okay, so generalized profile, Gaussian profile. Okay, now we have to create a fit. So basically, what will we are going to do is we will be creating some random data, okay, a noisy data that we did in our previous lectures. So we will create a noisy data and we will try to fit our ideal Gaussian on it. So for example, let's say this is the ideal Gaussian. Okay, so we will add some noise in it and we'll try to make a model that will try to best fit these noisy data. Okay, so for example, why we are doing this is because we have the noisy Gaussian distribution in the form of spectrums. Okay, so we will try to find what is the best value for the ideal distribution for that noisy data. You guys understand this part, what I am trying to say? So, do you get it what I tried to say? We have the like very noisy data in the form of spectrum, which is the noisy Gaussian distribution, and we try to fit our model to get the ideal form of normal distribution onto the spectrum so that we get the best ideal spectrum for that particular galaxy. So, let's say I'll show you one example. So, okay, so it's if this works. So yesterday also we were having a spectrum. Okay, so we have this spectrum here. So we'll use the same spectrum of that or that same galaxy. I'll try to show you what I am trying to say. I'll just fastly import Astropy from astropy.io. Import fits, then fits.open this, and then we have this as one, which is spec data, and now flux will be is equals to spec flux, and wavelength will be is equals to spec 10 to the power this log lamp. So I remember that it was in earlier it was in first table, so I assigned the index for the first table here only, and I remember there were two columns inside it, flux and log lamp. So I just rapidly did that. So now I will just plot this flux wavelength on x-axis and flux on y-axis, and then I will plt dot show. So okay, so it gave me some error. Just a second. Spec dot data. So yeah, we are correct, I guess. So what's the error then? Bin table HDU object is not scriptable. Okay, why is this error coming? So I don't think this should come. Flux. There is a table flux here, and okay, just a second. So there is some type error. I'll just check what we did yesterday. Wait, I have this in my local folder. So yeah, we did the same steps, I guess. Uh, what if we tried not to make it short, but I just try to do something like this. Spec is equals to data and then spec. Okay, so it worked like that, but I have to find why was it not working earlier when I was using the shortcut. Rather than writing this whole thing here, I just made the index here because it must work. However, I will write it like here only that it's given non-scriptable error, and I'll tell you why that error was coming because it should not come like that also. So basically, you see here there are some normal distribution. If I'll just use plt dot x limits from like 6,500 to 7,500. So this is the method to limit the graph. So you see, these are also the normal distributions. Okay, so as you see here, these are normal distribution, but they are noisy. They are not as smooth as these. Okay, so we have to fit the ideal distribution on Gaussian distribution on it so that we can get a best value for that H alpha wavelength. Okay, so this is our task. So this I will just delete it for now because I was just it was just for an example case. Now we will be writing the main model function, and then we will be importing some good spectrum because this spectrum is very narrow line. So I don't want to use it. I will use some broad line spectrum. So we have a very clear spectrum of some galaxy. Okay, so we will find that galaxy in SDSS soon. So I will define the function here. Let's say wavelength and flux and A1. So this is basically wavelength and friction because we will be like finding out some things here. I'll tell you soon. So now we have something A2 else A2A and M1 and M2 and W1 and constant, not constant, continuum. Then I'll just make it very clean. So just a second. If we can do something like I'll have to test this first because I'm oh, how this happened. Okay, I don't know how this. Okay, so we just got some things vanished. So pardon me. I'll just write it again. Okay, so it works. So let's say make it 50. So as I said, we will be doing the fit here. So we will be doing least square fit here. So basically now we will be using this thing, square fit. So in statistics, I will share notes with me. I have these Caltech notes with me somewhere here. It was, I guess so. Yeah. So these are very beautiful statistical notes for physics. And here we have every probabilistic graph, including the Gaussian and Bayesian distribution and all these things. So here on this chapter, sixth chapter, you can see least square methods and Gaussian likelihoods and all that stuff we are doing here. So basically, least square of it also has some formulas, which either way we can write it using normal Python, but now we have this curvefit here as a module which help us to just import curvefit and use it seamlessly without writing the whole formula for the linear fit. So we will be performing linear fit here. Okay. Now let's say the optimized parameters and convolutional matrix. Let's say for the fit will be is equals to curve underscore fit non-linear, because we will be importing the non-linear this time, because we have to make it realistic, and realistic one has more than one Gaussian, maybe two or three or something like that. So first we will be making our work for these two non-linear Gaussians, non-linear basically function. Okay, now we have the other parameters as a wavelength and flux, and there is something called parameter O, P naught basically. P naught will contain all the parameters which we want be changing. So we want this like as a constant parameter that will stay unchanged throughout the code. Okay, so however we will be assigning these parameters with some values. Okay, so we are clubbing this because these will not be changed anyhow in the code. So we'll add some error because I'll tell you because there will be some error in the calculations. So we want some what will be the errors in our model fitting. So basically we are just doing this linear square fitting here using SciPy. So it will be like square root of diagonalization of the matrix. So to know this, you just basically need some statistics and mathematical knowledge of the Gaussian, so which is usually we study in our BScs and MScs, I guess, in our coursework. So I won't be repeating that, but you can definitely go to this whole PDF. I will be sharing this, and you will get your fundamentals clear. So I just did the diagonalization of that matrix and did the square root to find out the error. Now I will print again these is equals to 50 times, and now again I'll use the print to printing. So this function is basically for printing out the best parameters we got. Okay, so this is basically for the spectrum, generalized Gaussian profile for the spectrum fitting. Okay, that's why we will be fetching here the wavelengths, wavelength one and wavelength two. Basically, the wavelength one and wavelength two will be the fitting wavelengths. So I'll show you from the graph what is this wavelength and the flux. So we have assigned here in the function. Okay, so because we will be needing that particular wavelength value, right? So the best printing out the best fitting parameter and one standard error. Okay, now it will be printing our values, which first will be a1 plus, this will be in the form of LLU optimized parameters. So now this thing is using some complex code of indexing. I'll tell you what is that after writing this whole code. Plus now this line is very important. Okay, so first of all, we are printing the A1 value, this amplitude A1 value with the optimized parameters. These are optimized parameters, which I said will not change. These might change because of the variation on these fundamental variables. So if these value changes, this whole will definitely changes. But if these changes, this will never change. Okay, so these are dependent on these values, but these values are not dependent on what is this. So we assigned it as a parameters. So optimized parameter with the zero index will be the A1, and error value for the same optimized parameter at index 0 will be the error for the A1 amplitude one. So we assign the error because it will definitely be some different values, of course, because there are many parameters, so there will be different values for the error also. So error at the 0 index in that array will be the error for this amplitude. Understood? So the error in the first place, error at the first place will be error for the A2, and then the third place will be the error for the uh, mean one. Mean one is basically wavelength one. Okay, so basically mean one will be somewhere like here. For example, here it was 5 and mean 2 will be here 10. So it will be the wavelength 1 and wavelength 2 basically on the spectrum, because on the x-axis of the spectrum we have the wavelength. So now we will be printing same thing here for A2, and I will shift the index to 1, and I will just edit A1 to A2 and shift the index to from 0 to 1, and I'll rewrite this as wavelength 1 and shift this index to 2, and I will write wavelength wave 1 error as this, and then I'll copy this thing here, and I will write wavelength 2 error with the index 3, and wavelength 2 error again, and error as index 3. Now we will finally write the width of these uh, plot. Okay, so it will be at the fourth position. Now, there is a catch. You might have a question in mind. Then why we have taken width to be a single value, not the multiple values? Because maybe in the realistic form, this width may be different. This width will be different. Okay, this can happen. The thing we are using here in astronomy works on this particular generalized way, where the width will has a standard value of a single for all things, but we can take width as different values based on our requirement for the complex problems also. Okay, so right now we will take it as the single width, because we will be also applying some continuum of which the wavelength will be equal for every like uh, distribution. Okay, so I will write here continuum. Okay, so just a second, just a second. Okay, I will write here continuum level, and then now I will make this as 5, continuum error will be at the 0 index, because continuum error is okay. So before that, I would like to show that we here assign the continuum as 3, and you see the plot is starting from this here 3 only. Okay, so the continuum error will be here defined as 0, index 0 error. Why? I will explain that when we will be plotting it. So I will here write a mention that continuum error is at 0 index because I'll complete it after we write the plot. After we make the plot. Okay, so I will again print these 50 values, and here I will print plotting model data over the observed data. Okay, now we have basically defined a function till now here, where we have defined the optimized parameter and the matrix and doing the square fitting and finding out the accurate values for A1, A2 and wavelength wave 2 and width and continuum level with their errors. Now we will be making a plot. Okay, so for this graph, just a second, we will be defining y model is equals to, okay, y model is equals to nonlinear wavelength multiplied by optimize underscore parameter. So this is a shortcut. So I just wrote the wavelength and multiply by optimized parameter, comma multiply by optimized parameter, and it will write all the parameters which is inside the optimized parameter. Okay, so basically this is a shortcut. Okay, now we will plot a scatter plot for our wavelength and flux and label it as data. Now we will plot y model and label it as our model, and because we need our data in the scatter and the plot will be a fitting line, so we just write here plot and data as a scatter, and color is equals to uh, purple. Let's see to define it properly. Okay, and here we assign the color is equals to black. Then we have to of course we have to use the vertical lines here to find out the exact value for the wavelength 1 and wavelength 2, which we will be using in the our real data. Okay, to get the exact value for the H alpha. So wavelength 1 will the first vertical line will be at the wavelength 1, so the optimized parameter at index 2 with y minimum is equals to 0, and y maximum will be up to, the line will be up to y maximum, which will be equals to the maximum flux value. Okay, so the line will start from y is equal to 0 and end at the top tip of the plot, which is basically flux dot max, where the flux value is maximum. Okay, comma ls line style will be is equals to this dotted, and color will be is equals to blue for now, and I will make another vertical line for our wavelength second with the third index, and rest of the things same. Since we use the label here, I will use the legend, and I will finally show up. Okay, now I will since we have created this whole function, now we will return all the things we need. We need optimized parameters, so we will be printing whole of these, and we will be returning our matrix. Okay, so we have this function here now. Just a second. Okay, so there is some syntax error, I guess, where okay, somewhere we did some mistake. Okay, so I also think that if we try to just erase this thing and apply the fifth, I just have some doubt here. What will be the value of the error in the continuum? I'll just check it out. So also y minimum is equals, okay, so it should be y maximum, y max. Okay, so finally our things are running right. I just have some issues. Error is not defined. Oh, sorry. We have not defined the parameters yet, so it won't be working. So I think based upon my observation, uh, the quantum error will be also at the index 5. If we are defining these parameters up to 6 parameters, then the quantum error will be similar in the array also at the 6 point, rather assigning it at some other index. It will be wrong if we will define it as the zero index error, because it will be error of amplitude and it will make some noises. So I think we have to define it as 5 only. So yeah. So now we'll be assigning some wavelengths. Wavelengths is basically the x units. Okay. So x values, which will be numpy dot length space for now. However, we will change it to the exact wavelength from the spectrum soon, and p dot length space from 0 to 20 only, 0 to 20 and 100 units. And then pure model. Pure model is equals to non-linear model with the wavelength has values wavelength test, and then we have the amplitudes like this, 5 and 10, and then we have a something like 1 and 0.25. Okay, so basically amplitude 1 has 20, amplitude 2 has 40, and uh, then we have the mean 1, 5 being to this, and then we have 1 as our standard deviation, and then we have this continuum and 0.5, okay, 0.25. Now we have to add some noise, okay, noise, add some noise to test our model. So our model is basically this, okay, these two lines, the square fit model, okay. These rest of the lines are only printing what our SciPy is doing at the back end while fitting our model onto our noisy data. So we will make a test function pure model, pure underscore model, plus some np dot random dot normal, and then I'll add some noise in it using numpy, comma, size is equals to length of this pure model. So Now I will be printing plt.plot wave test with test function, and then plt.show. So yeah, you see here. Now this is adding random noise. So every time we run this, it will change some noise. So if I do one thing, I do pure model here, it will be plotting this pure thing. So now we have to use it as some noisy data, just like original one. So it is adding the same length of the noise as the pure model, and adding some noise in the same array length to make it like work without any error. Because if the length of the error in the array will be different from the dimensions of the array of in the pure model, it will not be adding any error, and it will give the error. So we have this noisy data here, for example, right now. Now, since we have this data here, now we have to fit our model, fit our ideal data, so that what should be the median or something, the linear square fit for these lines, so that we have the best fit for this. So what will be the best Gaussian graph for this model if it works in the ideal case? Okay, so what will be the values? So now we will be just writing two things here: out pp out parameters and out of matrix, basically the output values, and now it will basically fit. I'll call this fit model, fit function, with the wavelength as test, that x-axis, model as this function, and then for example we'll set the values as amplitude. We have to just guess the amplitude. So I'll just guess the amplitude here as 16, however it is 20, and I will guess the second amplitude as 31. We don't know, so we'll do some guesswork. We'll Okay, so let's say the amplitude is right for this, and I will write these other things same. So I just mess up with these some values, these values, so that to check if our model will work fine or not. Okay, so it's a fit is not defined. Okay, so I write fits here. Okay, model observation. Okay, so it's creating some error here. So it says, however, it made the fit for the first one, but it's creating some error by setting the color maybe. So okay, so I have to go to this part of the line, and let's say it's here's some error. Blue. If I write this fully. Okay, so it worked now. So basically, I just change here to the full sentence, rather going from the shortcut to write C for colors and B for blue. So finally, what our model is doing, it's working fine, I guess. So it says that our amplitude is around 30, and it's saying, okay, so it's weird results. It's weird, uh, but it's fitting correctly. Okay, so it's fitting correctly, but we have some weird results here. Okay, so but but we have to check basically our wavelengths. Okay, so we have to check if our wavelengths are correct or not. These amplitude may be weird because we have bad guessing or something like that. If I'll just manage to make it more closer, it may be correct. But since we have very good guess for the wavelengths like 4 and 10, which were very close to 5 and 10. So it says that our wavelength, basically the predicted wavelength is equals to 4.9 with the error of 0.03, and it says the wavelength 2 is 10 with the error of 0.01, which is correct, and this is what I need for our plotting, for that fitting of the spectrum. Okay, so for now, I will not mess up correcting the model for finding out the amplitude and all that stuff, because our main model is working for the wavelength. So I'll keep this model for now without editing it, and we'll try now working this model, this same model on our spectrum fitting. Okay, now what I will do is I'll go and find out some real galaxy, and download its spectrum and apply that model to find out the redshift of that galaxy. Okay, now just a second. Um, so this is not started. So I'll share the spectrum with you guys. Okay, so I think this definitely have no. This also don't have any spectrum studied. So maybe this one. Okay, why not? Object with spectra. So I have to do these things now. Okay, so this map is full of stars, but I need a galaxy. So we have this galaxy here. So if I go to explore, so this is the galaxy, I'll go to spectrum. So I have this spectrum here, and we have these lines of H alpha here. So we will just trim this spectrum from here to here. Now I will just go to fits file here. I'll share this ID, and here I will write fitting our Gaussian model over a real galaxy spectrum, which is equals to. Okay, so I think I would not have to write like this. I should not like this. Now, okay, I hope it must work. Yeah, I will just download this spectrum. So I have the spectrum here. I'll save that. Okay, I'll save that spectrum here, and I'll delete the previous spectrum from here. Okay, so now it's clean. Now I will be testing and plotting that spectrum first. Okay, so from astropile.io import fits import scipy dot signals as ss. So basically we will be using it for some purpose. So I will be telling why we'll be using it. So there is something called, so we will be using it to guess out the best signals. Basically we will be using it for guessing the values. Okay, so right now we know what was the original value, so we just guessed it right. Okay, so what we will be doing is we will be using the signals to find out the peak, and only cut out that signal, only plot this, only fit this spectrum or our model onto those peaks in that spectrum. So I'll show you how, basically. So no worries, I'll show you how. So now data is equals to fits dot open. Okay, wait. Then we have the spectrum data one dot columns. So you see, my spellings are wrong. Wait a second. We have this flux column here. Now finally I will plot flux is equals to data1 dot data as flux, then wavelength is equals to 10 to the power, because it's in, oh sorry, because it's in log, data1 dot data, then log lam. So whenever you are working with some spectrum, it is not mandatory that the flux will be written simply as flux, and the log lam will be written, the wavelength will be written in the form of this log lam. So you have to find that yourself, because under some guidance of that telescope or something, to find out what is the accurate abbreviation used for the wavelength and all that stuff. Now PLT dot figure size. So let's just not do that for now. Wavelength dot flux and comma flux and line width is equals to, okay, so let's do it here only. Okay, so we have the spectrum here, but it's so messy that we have to change the line width. Okay, line width, let's say 0.3, okay, 0.3. So you see we have the spectrum, and if we try to compare it here with this spectrum, we see around 7,500 to 8,000 we have this H alpha here. Okay, so it must be somewhere here. Okay, these lines. So we will limit the spectrum finally. Okay, so what I will do is I'll just write here plt dot figure and then fig size is equals to 10,5. Okay, so now we can see it more clearly that our this H alpha is somewhere here. Okay, as seems from here. So there is a dip here, and then O1, and then nitrogen doublet, and then we have our spectrum. So we have a dip here. Okay, so I have to check it properly. So after looking carefully, okay, so we are working on this galaxy, right? So wait a second, what's not matching with our, okay, I'm doing one thing again. I'm just re-downloading that data and I will plot it again. Okay. So I think there is some, okay, the data is same, however, and I'm not actually able to identify it because lines are very short. However, what I will do it now is I'll just apply some limits here. PLT dot X limit from 6,000 to 8,500, let's say, and I have to write it before plotting. So now what I will do is, this is good, and you see here we have a dip for, okay, so we have this dip here, and then we have a peak. So basically, I think for our first spectrum, we need to change a spectrum because most of the lines are having the same height. So we are like we will be messed up for making a best pipeline for a journal pipeline for every galaxy if we choose the wrong reference galaxy. So first of all, what I will do is I will find a accurate galaxy which have a good H alpha peak and visible peak, so that we will not get messed up like this in our first reference. So I'll just zoom out and find some other wavelength of the galaxy, spectrum of the galaxy. Okay, no. So these are actually the distant galaxies, so they have a long redshift. So H alpha is very much shifted from its actual position. So yeah, we have a good one here as a reference. So we will take this galaxy with 0.09 redshift. It's quite large. In the sense, it's quite low because in the sense spoke that it's very large is like it's quite far away. Okay, so not far away actually. I was wrong that time. So I'll just download this. I'll just drop it here. Okay. So where is, yeah, you see the peak of H alpha is here. I'll just cut it out here also. So I'll just cross this. So I'll cut out the wavelength from 7,000 to around 7,500. Okay. So I'll change the link also. So it will be 7,000 to 7,500. So you see we have this. I'll cut it more. I'll cut from 7,200. Oh, 7,200 to 7,000. Okay, so 7,210, 100, and let's say 50. Okay, so I cut it a lot. Let's say I cut it to here. 2,200 is best. So we have these peaks here. I'll just make it 30. Okay, so we have this H alpha peak here, and these we have the other peaks here, but we have to only consider this. Now I will use the signal to cut out the signal of a threshold height. So I will define the height to, for example, 20, so that the signals above 20 will only considered in our graph. The other signals below it will be demolished. Okay. Now, what we can do instead of doing the signals, we can just define the limit from 17180 to, okay, 7176, I guess, to the this limit. So now you see we have only two plots, so no need to apply the signal value. However, we will apply the signal value above 20 because there are some minor signals here, so that it doesn't consider that for fitting. Okay, now just a second. So since this is a close galaxy, because its redshift is very less, we will verify it. Now we have to fit it using our this model. Now we will write our fitting thing. So since we have this cut out, now we have this is actually only for this program. So we have to save this thing here. How will we do it? Like subsection or you can say subsection, yes. Or what we I am not getting the word in sets subsets. Okay, yeah. So subsets where so np.where is basically help us to limit and save it where wavelength is greater than 7180 7176, sorry, to be precise, and wavelength is less than 7230, and then flux will be is equals to subset of flux will be is equals to its corresponding flux in the subset, and similarly for wavelength. Now plt dot plot sub underscore wave comma sub underscore flux. So what we basically did was we assigned some variable to save this data, okay, as subflux and sub that, and now you can see we have a very beautiful plot here, okay, which we can use to do fitting. So this is our real data. So you see here that it is very similar to our this plot. However, this is more noisy. So since our fitting is very perfectly fitting on our that much noisy data, since this is not that much noisy, it will fit more likely to be perfect. Okay, so it will fit more perfectly. So now flux peaks. I will definitely gonna use the signals one to ensure that there should not be another signals. For example, sometimes what happen there are two signals here. For example, I just want to consider this signal. So let's say, however, in our case there is no extra signal which is disturbing our plot. So let's say we have this signal, very good. Then we have this signal, but there is one more signal going up here and then coming down. So there will be total three signals. Okay. Whenever there are three signals, we cut out the shortest one and take those another left signals to make the Gaussian distribution. So now I will just write this thing. You can use it whenever you get that type of signal, that type of disturbance. But right now I will write it and give some values height is equals to, since we don't have any disturbance signal, I will just assign the value that the signals above 20 will be the good signals. Okay, so that can be considered, and I will assign it as 0. So this is the main thing you have to like do using the signal parameter signal function of SciPy. Okay, so it help in that way. Flux underscore peak current means. So means will be basically these exact wavelengths. Okay, so it will be the exact wavelengths. So the mean is basically the wavelength at which these peaks are happening. So it will give us exact wavelength of H alpha and the another one. Another one is basically the N doublet, nitrogen doublet. So you see, now, there is a catch. You can either calculate it using the nitrogen doublet, otherwise you can calculate using the hydrogen doublet, any one of it. Okay, So since hydrogen alpha goes a bit longer and very good recognized, so we use this. Uh, that's why. Otherwise, we can use all of this to find out the redshift, but these are normally mixed in the other signals, other disturbances. So we prefer to find out the redshift with H alpha for more accuracy. Okay, just that's why. So till now you have any query? So do you have any query? Otherwise we will just run this. So any doubts till now? You can write. I'll just afterwards we have to write the redshift formula and we are done with today's lecture. Any doubt till now? So yeah, we are finding the observed wavelength using the Gaussian parameter without using the interactive spectrum we used to do in our previous function. So today we just plotted this Gaussian function using NumPy and try to create a model for our function on our disturbed function. We created a noisy function, simulated noisy function, and try to fit our model, Gaussian ideal Gaussian model, on that simulated function. And we found that it is giving a very nice value of wavelengths and wavelength 2, which is what we need. And now we are applying that model to our this wavelengths, spectrum, the original spectrum. So we found it to be near to accurate, I guess. So if I just open, I'll just cheat a bit and find if our model was working perfectly. I'll just open the interactive spectrum here, and I'll just zoom. Okay, so it's taking time. So okay, so I'll just zoom to this part of the spectrum, and I'll find that it's saying the H alpha peak is at 7198.52, whereas our peak is at 7187.86, which is near to what the interactive spectrum sees. So this is how we calculate it. Now the final thing is we print out the fitting model for it, like we did it for the simulated part. So till here it is clear. Is it clear? Okay. So I'll print conv matrix underscore. Then I'll apply the fit on this part. Here it will be sub underscore wavelength as x-axis and flux will be sub flux and amplitude will be, let's say, I don't know what to take it as amplitude. Just a second. Okay, so I'll just guess it to be 20 and 40, let's say. And now 5. Okay, the mean will be means and 1 and let's say 5. So okay, so we have this here. You see our guessing was incorrect for the amplitude 1 and amplitude 2. However, we don't need it. Also, our guessing for the continuum and width was also not that correct. But since our guessing was correct for the means, it gave us the correct wavelength with the error also. It says it gave us the accurate wavelength. So the guessed wavelength was 7187.86, The accurate one is 7187.946. Okay, so if we see the interactive spectrum here, it also says something like this. Okay, so it says 7187.86. Okay, now our spectrum says, which was earlier was guessed approximately right, but it also gives some error also, that due to noise the best fit line will be best fit wavelength will be this, with some error this. Okay, just to get the accurate value for the fitting model. Okay, so it fits the plot here. So basically, when we assigned the 20 here, it just cut off all this value and made the very smooth plot. Okay, it made a smooth curve here by joining these two peaks. Okay, so it cut off all that stuff. Now, your task final is hashtag your task. Since we have the wavelengths now, since we have the accurate wavelengths, wavelength 1 or wavelength 2, you can take any of the wavelengths, either H alpha or nitrogen doublet, and find out the redshift for this galaxy. And your answer will be is equals to answer must be this, around this. Okay, so I'll just leave the column here, def red redshift, then lam observed and lambda theoretical, and your function here. Okay, so your function here, write your function here. Okay, so okay, it must not work like this. Okay, so I'll just okay, so your function here, just make it code and write the function and then run it. Now, so we are done with today's work. So if you have any query, I'm open to solve. Otherwise, I'll share this PDF, this notes, where you can revise your fundamentals of Gaussian profile. Okay, and there are probabilistic matters, Bayesian theorems, and all that stuff, more than what we learned today. It is a huge treasure of statistics, and it was shared by my professor at IIT. And this is a very beautiful notes by someone at University of Bologna. It's Bologna, Bologna, I guess. Yeah. So it's Bologna. So it's very beautiful notes. So you can just go and have a read to it. So if you have any query, you can ask. I'll just turn off the recordings. Thank you.